Welcome everyone. This video is going to go through the two video assignments for chapter 14 and 15, parts 1 and 2 respectively. So we will dive in and get started. So the first section, part 1 and part 2 of part 1 of 14 and 15 was focused on confidence intervals. So the first question asks, why do we use a confidence interval? And the answer is, or that I would use, is something along the lines of to estimate the range of the true unknown population mean. Unknown in parentheses, close that off. Population mean. Okay, we always know the sample mean from a data set, so x bar, right? And then what we're doing with that is constructing a range that might contain the population mean. Again, the population mean is either in there or not. We don't really necessarily know, but we're trying to predict with some level of confidence, right? And then to do this, right, what conditions need to be satisfied? Okay, and you're going to see these conditions pop up a lot. First, we need the observations, so the x sub i's, which are the observations, need to be IID. Okay, independent, so that stands for independent and identically distributed. Okay, the last bit, identically distributed, is almost always satisfied if you're sampling from the same population. If you were to say, look at if your population is geriatrics, right, and you sample from, say, Minnesota compared to California, those are going to be not identically distributed. But if you're sampling within one population, generally that identically distributed is going to be satisfied. That independent piece is a little bit trickier to establish, right? We know what independent means, where one event isn't influenced by the occurrence of the other one, right? So we just have to go through that mathematical process, which is why we needed to talk about independence earlier in the course. Next condition is that for Z confidence interval, we need the population, or the population that we're looking to follow a, I'll just say I'll just write it out in words. Population is normally distributed. Okay, we need this condition. Later on, we will relax it, and the relaxing condition will be that the sample size is greater than 30. Okay, so eventually we can use that. Here we do need normality. Okay, so I'm just going to delete that out. Okay, and the third thing is that the population standard deviation, which we use as sigma, is known. Okay, next week we will change that condition to unknown, and then we can do a different type of test. Okay, so we need those conditions. Always need to check those conditions before we do any calculations. Don't do calculations willy-nilly from here on out. Outline the process. So first, we should check conditions, right? And I say that a bit tongue-in-cheek, right? We should always do that before we're actually doing it. And then when we go on to create it, then we need to find x bar, okay, which is the sample mean. Sigma, we need to figure out what that is. N, which is our sample size. And then we also need to know what alpha is, our significance level, okay, because then our confidence is 1 minus alpha, okay? And then after that, we're going to calculate E, which is our margin of error. Now there's two ways to do this, and I encourage you to make use of both. The easiest version is if you have Excel handy. I would just do confidence.norm, and then the syntax that you need is alpha, sigma, and then n. Okay, and you're going to enter those quantities in that order. So that's why number 2 is important, because you need to do those things. The other thing that you can do is, if you're doing this by hand, maybe I'll do this on a new line, E is equal to this Z subscript alpha divided by 2 value times sigma over square root n. Okay, and Z alpha over 2 is described how to be found in the notes. One thing that I've always given students that is kind of handy for them is a little table. And I'm going to do, I think that will suffice. Okay, so if you, this is really too much for me. Okay, I am also, if you don't know this about me, I really like formatting things, and you can maybe tell that from the course materials, but I like to make things look presentable. Okay, so we want, I need alpha in one column, and then I need this Z alpha over 2, and I am too lazy, I'm just going to copy paste that in here. Okay, so we want for 1%, for 1% significance, 5% significance, and then a 10% significance level. Okay, for 1% significance, the Z alpha value that we're going to use is 2.575, I think, ish. Okay, the 2.57 is really what you need. 5% is 1.96, 1.96, and the last one is 1.65. So as we actually get a larger alpha value, the Z alpha becomes smaller. Okay. I give you these values only because these are from the standard normal distribution. These are going to remain fixed. So if you ever want to calculate this by hand as opposed to using Excel, use these values in this calculation. And that literally, like, so this entire entire value, if alpha is 5%, is 1.96. Okay, just so we're crystal clear on that. And I think there's one more question. Let's see. So once a 95% confidence interval is created, what does it mean? Okay, so that's the interpretation piece. And we know that the interpretation is we are 100 minus alpha percent confident that the true population mean is in, the confidence interval we made x bar minus e, x bar plus e. Oh, I should actually maybe add that. Check, calculate e, and then, yeah, we should always say construct CI confidence interval and put that there. Okay. Back to the interpretation, right? If repeated, so true population is in the one that we have, and then if repeated, and we create 100 whatever percent confidence intervals, we would expect 100 minus alpha of them to contain mu. Okay, and so this is the generic one, right? You have to figure out what alpha is, and then also the other thing is that in the interpretation, if you're in a context, right, you should change what mu is. All right, so confidence intervals, students generally like finding them because it seems pretty darn easy. The tricky piece is honestly in the interpretation, right? Confidence intervals, the true population mean is either in the one that we have or not, with a certain level of confidence. If we're looking at sample mean, the sample mean is always in the confidence interval because you have to center it at x bar. Okay, so with that said, we're going to move on to part 2. So part 2 is now where we do the one sample z-test. So we have an SRS of 52 individuals, determine that x bar is that. Individuals come from a population where the quantity of interest is normal, standard deviation of 2.5. We are interested in testing the claim that the mean is less than 34, conducted tests using 10% level of significance. Null and alternate. Okay, so we have null. And then we have alternate. Okay, so both of these are going to look like mu is something. And so in the null, you might remember this, always equals in the null. Okay, what I'm going to look for is the claim, right? The claim is always the alternative hypothesis, and that is this the second to last sentence. We are interested in testing the claim that the population mean is less than 34. So I'm going to put in my alternative less than 34. Okay, and the value that we use in the alternative goes in the null as well. Okay, and then any symbol that I use, I should also define. So mu is equal to population mean of quantity of interest. Okay, so just make sure to define it. Okay, and certainly you can write these in words if you wish. I just find with this stuff it goes quicker in symbols. That's me. So there we go. Determine the value of the test statistic. Now, test statistic is a z test statistic, so we're doing a z test. So typically the test statistic is named after the test statistic or the type of test we're doing. Then z here, fraction, numerator's x bar minus mu, and then I should actually do mu sub 0. Okay, I'll explain why in a moment, and then the denominator is s divided by square root of n. Okay, now I'm actually skipping a step here, much like the confidence interval piece. Before we do everything, we should check conditions. And so what are the conditions we need to check? Actually, they're the same as our confidence interval conditions for this test. Okay, every test is going to have conditions, so I should check these 3 conditions before I proceed doing the z test. Okay, but there we go. Okay, now I said I was going to talk about mu naught. Mu naught, the reason I call it mu and mu naught, so mu is the, truly, as we said, the population mean of quantity of interest, right? So that's in the hypotheses. The 34 that I'm using is actually what we would call mu naught. It's the hypothesized value of the population mean. So we think the population mean is 34, right? And so I'm using that as a placeholder. We might actually do this test and say, oh, hey, we don't have that evidence, right? And then we have to come up with we have to do some research and figure out a new value. Okay, so anyway, if we want to determine this test statistic by hand, we can do it by Excel as well. We can do, let's see, x bar, it says it's 32 in the numerator, mu naught is 34, s is, not s, that should be sigma for this test. Next week, it'll be s. So we do sigma, okay, so sigma, population mean, or population standard deviation, 2.5. Okay, 2.5 divided by square root and 52. Okay, and this is where I would need to get a calculator, and I will explain how to do this because your calculator will lie to you. Really, what is happening is that order of operations is giving you a hard time. So I'm going to pop over to Excel. Okay, I'm going to write x bar mu 0 sigma n, and so I'm going to do, this was 32, this is 34, sigma is 2.5 and n is 52. Okay, so now I'm going to do, for the test statistic, I'm going to do numerator and denominator. So numerator, and I know you could probably do this all one line. I am strongly, please, strongly encouraging you to do this by numerator and denominator separately and then divide the two, because order of operations will mess with you. Denominator is sigma divided by square root, sqrt, squirt, 52. Okay, there you go. And then, so then our test stat is just going to be numerator divided by denominator. Okay, so this negative 5 point whatever number. Okay, and I can go back and put that in here. So I'm just going to say approximately. I'm going to continue to do everything in Excel. 5.76-ish. Okay, ish. And now it says provide the p-value, right? Back in Excel, I can only ever get the p-value using Excel because it requires us to do a version of norm.dist. Oh wait, which one do I want? I want regular norm.dist because of the direction of my alternative hypothesis. It's less than 34. It's to the left, right? So then I have to use normal norm.dist. I would use 1 minus norm.dist if it was greater than. Let's see, so then, and then also there's the 2 times version. See the notes for more details. In this version, I would do norm.dist test statistics 0, 1, and true because I'm working with the standard normal distribution. And I get a p-value that when you see this e, it just means it's like, it's scientific notation. And so that's 8, so it's decimal point 8 preceding zeros, and then 3, 9, 8, whatever, right? So super small, super tiny. And so I think I can wrap this up now back here. So I'm going to say P is approximately 0.12345678398. Okay. And yeah, we did it in Excel. I'm not going to worry about it. Now, moving on. P-value is super small, so we tend to say that there's little evidence for the null hypothesis, and so we have sufficient evidence for our alternative. So now which of these choices is correct? Let's see. So we are going to say we don't believe the null. That would be okay. Reject the alternative. Our decisions are never about the alternative, believe it or not, so we're never going to use those. Okay, so just delete those out of your vocabulary. And then the other bit is we never, ever, ever use except, prove, anything that's certain in in statistics, because ours is based on the data. But the other thing we can say is that if we find evidence for our new claim, we can say that our data, hey, there's something weird going on here. We need to continue to investigate. The data that we have are statistically significant. There you go. And then the last bit here, type 1 error or type 2 error. So if we reject the null, type 1 error, okay? Type 1 because we rejected the null hypothesis when it could actually be true. Now, we don't know if there's actually a error occurring, but we're just saying, hey, in making this decision, this could be the case. And we always want to acknowledge that. Okay, so there we go. We have gone through the confidence interval for a z confidence interval, and then also the z-test using a test for the population mean. All right, so now you're ready to get started on the activities. Enjoy.